Welcome to the debate. Our focus today is on, well, one of the most significant geophysical events of the decade, the eruption of the Hale-Gubbi volcano on November 23, 2025, in the Afar region of northeast Ethiopia.
And what makes this so extraordinary, really, is not just the scale of the eruption, but the context. This volcano's first recorded activity in approximately 12,000 years.
Exactly. 12 millennia of silence, broken so violently. That's precisely why it captured global attention. We're talking about a massive ash cloud that punched, 14 kilometers into the stratosphere?
It crossed the Red Sea, impacting air traffic and population centers far beyond the immediate blast zone. It was a complete anomaly that demanded an immediate scientific response.
Right. And that anomaly forces us to ask a really critical question about its primary scientific significance. Is this event most important for what it tells us about long-dormant shield volcanoes, fundamentally altering our global risk assessment? Or is its greatest importance found in its specific location as a definitive indicator of accelerated geological change within the East African Rift Valley?
I'll be arguing that the volcanological implications are absolutely paramount. This event is a wake-up call. It forces a global risk reassessment and compels us to redefine what dormancy even means. The explosivity is the core lesson here.
And I will be arguing that while the hazard is, of course, undeniable, the deeper scientific truth lies in its tectonic context. This eruption provides critical data confirming the massive active forces that are literally driving continental breakup in Africa. So, from my position, I see why you focus on the explosion itself. But let me offer a different perspective. I believe the Hale-Gubbi eruption is best understood as critical empirical evidence of these massive active geophysical processes within the East African Rift Valley. You can't separate the event from its location. This volcano sits directly within one of the most active rifting zones on the entire planet, where the African plate is slowly and sometimes violently separating. This process is literally tearing the continent apart, and it's facilitating the formation of, new land. The fact that this tectonic process reactivated a magma system after 12,000 years of quiet proves the underlying engine is immensely powerful. The scientific insight here about the rhythm and volatility of continental rifting, I think that is the paramount finding. It's what will guide all future research in the region.
That's an interesting point, and I see the connection, though I would frame it very differently. While the tectonic setting, it provides the plumbing, the truly critical scientific lesson here is the unexpected behavior of the volcano type. Hale-Gubbi is a shield volcano. Our entire system of risk classification is built on the premise that shields are known for, quiet, effusive lava flows. They rarely generate these high-magnitude ash plumes.
Right.
And yet, this event produced a devastating 14-kilometer-high ash cloud. That suggests a volcanic explosivity index far beyond what our models would typically assign to a long-dormant shield. This isn't just a geological curiosity. It's a profound threat management failure in waiting. So, I'm sorry, but I just don't buy that confirming a known process like continental rifting is more significant than the immediate hazard surprise this event delivered. This eruption forces volcanologists worldwide to admit that dormancy and a safe volcanic type don't guarantee anything. That has to change how we model risk for every single long-sleeping shield volcano on the globe. Okay, so let's delve into that, because the unexpected explosivity is the anomaly that rewrites global risk profiles. When we look at the data, the plume height, the ash spreading all the way to Yemen and Oman, we are seeing a fundamental challenge to volcanic typology. Most shield eruptions are VI 0 or 1? This was demonstrably higher. The source material says the ash covered local villages like black snow. That level of deposition, that kind of regional spread is completely counter to the classic definition of how a shield volcano should behave. For risk assessors, for emergency planners, the key lesson isn't where the plate boundaries are going to be in 10 million years. It's that a volcano we've classified as a shield can still deliver a devastating, high-magnitude event that threatens air traffic and infrastructure hundreds of miles away. That shock requires immediate operational change.
I see why you think that. And I agree, the hazard is shocking,
precisely because it defies the expected typology. But we have to ask why. Why did the shield volcano act so explosively? Because that reason, fundamentally, it points right back to the tectonic engine. The ash cloud is the outcome, the mechanism is the real scientific insight. So why didn't Haley Gubby behave like Hawaii's Kilauea? Well, the answer is the rift environment. The energy for that plume came from the fact that intense faulting and extension from the rifting process provide these super highways for magma to ascend incredibly rapidly. And that rapid ascent means the volatile gases inside the magma, the water, the CO2, they have less time to escape before it reaches the surface. It arrives pressurized. Furthermore, the Afar Rift is just riddled with faults and hydrothermal systems. So this rapidly ascending pressurized magma likely hit significant groundwater reservoirs. And that interaction, a phreatomagmatic component, is what turbocharged the eruption, giving us that massive anomalous 14-kilometer plume. The explosivity is really a secondary consequence of the tectonic driver. The finding isn't just that explosions can happen, it's that rapid extensional tectonics create the perfect conditions to turn a typically quiet shield into an explosive hazard.
That is a compelling explanation of the mechanism. I'll grant you that. The tectonic setting provides the conditions for the violence, but the practical conclusion remains the same. Scientists now have to accept that this specific combination, a dormant shield volcano in a rift setting, is a high-level explosive threat, not a low-level effusive one. The scientific community just assumed this setup led to quiet fissure eruptions or slow lava flows. Haley Gubby proves that the classification of shield is basically incomplete as a hazard indicator once you factor in 12,000 years of dormancy and active rifting. The classification system itself failed us.
Okay, let's turn to the dormancy aspect then, because I think that 12,000-year gap actually reinforces my argument about the deep time scale and volatility of the rift. And I fully acknowledge 12 millennia is an immense period of quiet. It's outside of all human history. But from a geological perspective, the fact that this process, the continental breakup, could reactivate a system after such an enormous gap, well, it just reinforces the immense vitality of the rift system. We are talking about a system that started developing 25 million years ago. Its processes are cyclical, and the sudden reawakening of Haley Gubby confirms that rifting is not just a slow, continuous creep. It's a living, volatile system capable of these sudden, massive bursts of energy. And that finding is critical for tuning our long-term models of continental evolution.
That's a compelling argument, but have you considered the practical implications of that 12,000-year gap for, modern society? For global hazard mapping? Geologists often define a volcano as extinct or safely dormant based on eruptive history within the Holocene, so roughly the last 10,000 years. Haley Gubby just shatters that threshold, right? We now have definitive evidence that a system can sit silent for 12,000 years, completely outside of historical memory, and then produce a major cross-border catastrophe. The source material states no volcano is just dead. And that's not some philosophical musings. It is a critical directive for hazard mapping, for urban planning, for infrastructure risk assessment worldwide. We have to revise risk assessments for all these potentially active, long-dormant shield volcanoes globally, from volcanic fields in Europe to the vast shield structures in the U.S. Cascades. The societal cost of that revision, I think, far outweighs the value of simply confirming a tectonic theory we already had strong evidence for. And that immediacy brings us directly to the real-world consequences, which were immediate, severe, and transnational. The ash cloud did not stop at the Ethiopian border. We learned that the fallout forced the cancellation of multiple international flights across the region because of the severe risk of engine damage. This demonstrated that a single, long-dormant volcano can bring global air traffic to a grinding halt in a major corridor. And more acutely, the ash contamination ruined critical grazing land. It impacted livestock and livelihoods in an already fragile region. Homes were covered, water supplies were contaminated. This immediate high-impact hazard, the surprise of it all, that is the clear lesson. We can't downplay that demonstrable, urgent threat just to elevate long-term geological data that affirms a theory.
I'm not convinced by that line of reasoning because while the impacts were, of course, very serious, affecting grazing, water, and air traffic, the lasting scientific insight transcends the local hazard. The practical consequences, while tragic, are predictable outcomes of any major eruption. The real discovery lies in the scale of the power that was delivered, which confirms something fundamental about our planet's future.
Or immediate devastating hazard assessment, there is clearly much more to explore here.